everyone. This is group 7, and then we are presenting on differential equations. So let's get started. Now, let's look at the definition of differential equations. So, problems in engineering, the physical sciences, and the social sciences, when formulated in mathematical terms, require the determination of a function satisfying an equation containing the derivatives of unknown function. Such equations are called differential equation. In calculus, a differential equation is an equation that involves the derivative an an dependent variable with respect to an independent variable. When an equation involves one or more derivatives with respect to a particular variable, that variable is called an independent variable. A variable is called dependent variable if a derivative of that variable occurs. Consider the differential equations below. dy dx equals f of x. Here, x is an independent variable and y is a dependent variable. Let's look at order and degree of differential equations. Order. The order of a differential equation is the order of the highest derivative appearing in the equation. dy dx equals 3x plus 2. The order of the equation is 1. The square y over dx squared, that's the second derivative, plus 2 dy dx plus y equals 0, and the order is 2. Now, degree of differential equation. The degree of the differential equation is the power of the highest order derivative, where the original equation is represented in the form of a polynomial equation in derivatives such as y prime, y prime prime, and y prime prime prime, and so on. Example, suppose the square y over dx square plus 2 dy dx plus y equals 0 is a differential equation. So the degree of this equation here is 1. See some more examples here. dy dx plus 1 equals 0. The degree of this function is 1. Y prime 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 to the power 3 plus 3y prime prime plus 6y prime minus 12 equals 0. Degree is 3. dy dx plus cos dy dx equals 0. It's not a polynomial equation in y prime, and the degree of such a differential equation cannot be defined. Now let's look at types of differential equations. We have ordinary and then partial equations. We have first order, linear, homogeneous, inhomogeneous. We have higher order and nonlinear. Now, ordinary differential equation. An ordinary differential equation involves function and its derivatives. It contains only one independent variable and one or more of its derivatives with respect to the variable. A few examples of ordinary differential equations are as follows. In square y plus dx square plus k square y equals 0. The square y over dt square plus dx square over dt squared equals x. Partial differential equations. Partial differential equations consist of an unknown function with two or more independent variables, as well as the partial derivatives of this function with respect to the independent variables. Partial differential equations examples. So we have the heat conduction equation. We have the partial derivative of t of big T over the partial derivative of small t equals to the constant C, partial second partial derivative of big T over second partial derivative of x squared. Then we have the Laplace equation. We have delta square phi equals second partial derivative squared phi over partial derivative x squared. Okay, so yes, and then plus partial derivative square phi over partial derivative y square equals 0. Now we have the wave equation of a vibrating membrane. We have partial derivative square u over partial t squared equals c bracket partial derivative square u over partial derivative x squared plus partial derivative square u over partial derivative y squared. Then we have difference between partial and ordinary differential equations. So we have sine 2x plus e exponent 2y dy dx equals 0. Then we also have y square partial derivative of y over partial derivative of x plus xy partial derivative of x over partial derivative of y equals x squared z. Then we have linear differential functions. An nth order differential equation is said to be linear if it can be written in the form that is dx over dy plus p1x equals q1. It satisfies the following two conditions. 1. The dependent variable y and all its derivatives in the equation are of the power 1. 2. All the coefficients in the function are either constant or depend only on the independent variable x. If any one of these two conditions is not satisfied, then the DE is said to be nonlinear DE. So we have linear differential equations and we have some examples of linear differential equations. So dy dx equals 3x plus 2 d square y over dx square plus 2 dy dx plus y equals 0. dy dt plus y equals kt. Now we have nonlinear differential equations. It is second degree or higher with respect to dependent variables and its derivative. For example, we have partial derivative square u over partial derivative x square plus 4xy partial derivative square u partial derivative y square plus u equals 2 open brackets partial derivative square u over partial derivative x squared all squared plus 4 plus partial derivative cube u over partial derivative x partial derivative y squared equals 10x. How are differential equations useful in real life or the applications of differential equations? Now we have falling stone, y prime prime equals g, the constant. You have parachute, is velocity, water level, outflowing water, these are principle of differential equations, displacement, vibrating mass on a spring, beat of a system, current I in an RLC circuit. So this is the end of the presentation, and then we'd like to say a very big thank you.